With that, let me begin by acknowledging a profound debt at first. Uh, I essentially stole the words from William Blake, who, as you know, was a rather revolutionary poet of early Renaissance, from his book Songs of Experience. Tiger, tiger burning bright in the forests of the night, what immortal hand or eye dare frame thy fearful symmetry? The words in red are ones that you will have time to recall during the rest of the talk, and they do carry rather special meaning for this particular talk. For those of you who may not know what plasmas are, I think most of you do. It is known as the fourth state of matter after solid, liquid, gas, and in its fourth state, plasma is abundant on planet Earth. You see it on your plasma TV, which have now been replaced by other things, fluorescent light, the plasma lamp, the plasma gun, and you also see spectacular plasmas through the northern lights. If you have ever been so lucky as to go to Alaska to actually watch the winter skies, and it brightens up periodically to show these magnificent lights. They used to be thought of as dragons in the minds of many before scientists took arduous adventures, often at great risk to themselves, to figure out that they were actually a form of spectacular display caused by ionized gas. You know of the flaring sun. It's now become very real to us thanks to the excellent missions and observatories. And of course, further out among astrophysical objects, you have objects such as the Crab Nebula and many more, which remind us of the presence of plasmas everywhere in the universe. If you are going away from the Earth and you're going at a farther distance, seen from space at night, the United States is aglow from sea to sea, and many of you may or may not know this, thanks in large part to plasma lights. The reason I highlight all of this is the journey of plasma physics as it began in the 1950s with the fusion program, which I will talk about later, was responsible for a lot of the science that we have come to use in multiple ways. So even though fusion is still a little away, and I'll address that question, how far is it away? Uh, you should know that the journey has brought forth a great many beneficial effects to mankind, which surround us so much that we almost take it for granted. And low temperature plasmas, the contributions of plasmas to microelectronics industry are all things we take for granted, but these all came out as a spin-off of pursuing plasma science. And this was done not only in the realm of fusion, but as Sasha said in his introductory remarks, uh, there are things of great relevance in space and astrophysical plasmas, where plasma physics was also pursued as a discipline of great interest. I was talking to you about low temperature plasmas, and the subject has come along far enough that one can actually give a pretty succinct vision that seems quite realizable. And the low temperature plasma community ties itself very closely to the problem of sustainability on planet Earth. What they're envisioning is, in fact, that they would enable a future based on electricity through non-equilibrium plasma chemistry. Here you see solar, wind, and even fusion included as a way to get to lossless transmission. And once you have this power source, an exciting new vision for low temperature plasmas or LTPs is its use as a processor, as you see here written uh, uh, in the central box, uh, to use renewable resources and waste, convert them into valuable products. This vision leads to electrification of the chemical industry, as plasmas are ideally suited to be driven by electricity produced by renewable energy sources. And as I emphasized, including fusion in the future, and can be used for point of use of technologies. And those number of technologies are vast. They touch upon raw materials, chemicals and products, applications to healthcare and biomedicine, to plasma etching, semiconductor chips, and perhaps even to the construction of qubits for quantum computing, if it were to be real, and then the recovery of the resource, which can be recycled back. So there is a vision here of what low temperature plasmas might do for the universe as we move forward. Having said that plasmas are the fourth state of matter, we should pause and recall that actually that is a bit of a misnomer if you leave a planet Earth. In fact, Earth, where plasmas are the fourth state of matter, is the frail exception to the rule. Over 99% of the visible universe is already in a state of plasma. These plasmas are permeated by magnetic fields, which represent an enormous reservoir of energy. And as indicative of that, I'm going to show you a movie of the kind that you probably have seen, but now enabled for the exquisite images that have come down to us from Solar Dynamics Observatory. I was showing this to a friend of mine in Fusion, and he wondered whether I was showing him in a computer simulation or real data. And I'm pleased to tell you, as I was to tell him, that this is real data. And what you're seeing is uh, terabytes of data that are actually sent down from the Solar Dynamics Observatory. You can even download the SDO app, and you'll have a feast for your eyes every day at what the sun actually does. And I was referring to how the magnetic field of the sun is an enormous reservoir of energy, and you see the explosive power of that energy. And this now brings us to the subject of fusion, which is really the dream, if you will, to bring the sun to Earth. And that has been the dream since the late 1950s, early 1960s. To contrast fission with fusion, as you know, fission in fact means that one takes a nucleus that is large and breaks it up into pieces. In so doing, one liberates energy given by Einstein's formula. The mass defect, which is the mass that remains after you've broken up the fissionable nucleus into two smaller parts. Fusion is the opposite. What it does is to take two light nuclei, fuse them to form a heavier nucleus. And the reaction that is pursued most assiduously under controlled conditions of the laboratory is the fusion of deuterium and tritium. I am saying that we are trying to bring the sun to Earth, but I should quickly point out that the nuclear reaction that actually powers the sun is not deuterium tritium, but really hydrogen hydrogen, but that's also a fusion reaction. And so what we are trying to do is to mimic what goes on in the sun through the fusing of deuterium and tritium. And it turns out when they do that, you produce helium and a neutron, and the neutron is a very energetic particle, which can then be absorbed in a blanket and can produce heat, which can then be the core of driving a power plant. There are other fusion reactions which follow the same principle, which lead directly to the production of charged particles. And these more exotic nuclear reactions are very much a subject of great interest. It just is that to realize thermonuclear fusion in the laboratory, you have to meet certain conditions of density, temperature, and confinement time that are the easiest to meet when you actually have deuterium and tritium fusing. With deuterium being as abundant as it is in seawater, and seawater being infinite, virtually, as far as mankind is concerned. In fusion then lies, in a way, the ultimate energy source. And when you have heard the statement made, why fusion is an inexhaustible source of energy, that is what one is referring to. Before I get into the science of fusion and the science of stellarators in particular, I'd like to place our discussion in the context of some global perspectives of energy. We have had a change of administration, and all of you have noticed that the weather vanes have turned, that in fact there is a tremendous amount of focus on global warming, on energizing America. And this particular report that I like was actually put out by Columbia University by the individuals that are mentioned here during the COVID-19 period in anticipation of a new administration possibly initiating what they called a National Energy Innovation Mission. John Kerry at the time was not the energy czar. He was nowhere close as Biden hadn't won the election, but nonetheless, he liked the report enough that he actually wrote a laudatory note promoting it. But now that he is a czar of energy trying to implement Biden's policies, his endorsement undoubtedly means even a good bit more. So, what they might be thinking about, and what I like about the book is that it actually starts with some fairly simple lessons. This is not taken from the book, but this is actually taken from uh, a source that my kind colleague, Alan Boozer of Columbia University, shared with me. And this has to do with carbon dioxide emissions, which is a dire but simple story. The whole point of this simple graph is that if you look at pre-industrial times, we used to have fairly low level of ozone. And at about 1950 or so, things started going awry, took off very, very rapidly. This is post-industrial revolution, as you know. And now we are heading up where the world is producing 35 billion tons of carbon dioxide. The United States is responsible for about 15% of it. It's not negligible, but it is clear that this is a world problem. And any solution that we arrive at must therefore be a world solution. And this is where we feel that fusion, which is a worldwide effort, and you will hear about much that is going on, not only here, but in the rest of the world, you realize why it has, in fact, the potential to be really impactful. Uh, the time for pessimism is not here yet. You will notice that things have slowed down just a little, but not enough. It hasn't stopped growing, and this is the time to act now. So, how are we doing as far as US government programs go for solving the CO2 problem? And what this report does, the Columbia report does, is to look at DOE, which is perhaps the leading agency charged with controlling this. And as you know, we have a new Secretary for Energy, Governor Granholm, Secretary Granholm, who emphasizes solving the carbon dioxide emission problem and putting clean power on the grid as one of the driving forces in the DOE now. Well, if you look at what's going on in the various programs, the blue line shows you the baseline program. By 2017, the DOE research and development technology targets were more along the lines of the blue line, projected out till 2040. The yellow line is what would happen in terms of reduction of metric tons of CO2 if we double the DOE budget at the present time. That brings us only to the 40% level. And the point of this curve is that if we are striving to get to net zero CO2 emissions by 2050, you need to be on a curve, on a line which is far steeper than any of the lines that you've seen so far. And so this dotted line is what the Columbia University report advocates. They thereafter go on to project that if they would actually start out an emission now, with the federal government would on a $25 billion program to get on this line, then we will have some hope of really getting to a zero emission by 2050. But left to ourselves, even doubling the budget as it now stands does not do it. That's promising, that's worrisome. Worrisome because this is not just a DOE problem, it is a worldwide problem. And so all hands are on the deck to get to 2050 zero emission target that we are trying to chase, and not very well so far. Now, one of the quirks of the energy industry is that it has a character very different from pharma, computers and electronics, aerospace and defense, or the automobile industry. If you look at the research and development spending in global industries, and this comes from sources such as the National Science Foundation, is that what you will find is that 14% of major global industrial wealth is actually spent on improving pharma products, but over 11% in computers and electronics, about 7% in aeronautics and defense, automobiles about 3%. Look at energy, a pitiful 0.4 to 0.5%. This is not just a statement of the energy companies being greedier and keeping capital more to itself. The fact of the matter is that there are laws in place, regulatory constraints on energy industries that does not allow them necessarily always to take taxpayer money and boost up their spending on energy by a substantial amount without restraint. Undoubtedly, some of that is a matter of choice, but some of that is also the nature of the laws in the country which regulate what they actually do. Now, I don't want to let them off the hook in this case because between 0.4 and where they can go, there is still a substantial gap. But going to where the pharma industry is in computers and electronics, probably not one of their choices. Again, from the Columbia University report, of 46 energy technologies that are critical for deep carbonization, only 6 are progressing at a sufficient pace to avoid catastrophic climate change. This comes from the IEA. Roughly half of the reductions that the world needs to swiftly achieve net zero emissions in the coming decades must come from technologies that have not yet reached the market today. Energy innovation cannot match the rapid cadence of product development and commercial fusion achieved by software startups. New energy technologies, and this is really an important point and of great relevance to fusion, and not just fusion, often take decades of development and billions of dollars of investment before achieving commercial traction. While the rest of the country and other think tanks are thinking about uh, global warming and how the different technologies fit in, including fusion, and the Columbia report does in fact mention fusion among one of its 46 technologies, but doesn't give it very high billing. In the meantime, the plasma physics community, the fusion community have come together uh, through National Academy of Science, Engineering, and Medicine reports, NASEM reports, and I will talk to you very quickly about recommendations from 2 of these reports. The first one is the Berlin Plasma Research Report, which says that the United States should remain an ITER partner as the most effective way to gain experience with the burning plasma at the scale of a power plant. The second one was, and this is something that will interest you, that the United States should start a national program of accompanying research and technology, leading to the construction of a compact power plant that produces electricity from fusion at the lowest possible cost, bending the cost curve then away from the expensive ITER reactor, is something that is very much on the minds of the US fusion community. The key takeaways from this last report, which my colleague at PPPL, Rich Horeluk, chaired, are the following. The recommendations are for the United States to be a leader in fusion and to make an impact on the transition to a low carbon emission electrical system by 2050. The DOE and the private sector should produce net electricity in a fusion plant in the United States in the 2035 to 2040 timeframe. They pay attention to the fact that 2050 is the aspiration for net zero and for fusion to have impact. This is what we need to do on the 2035-40 timeframe. For those of you who think that fusion is 30 years away, the fusion community is now telling you we do not have the luxury of 30 years away. We have to get what we need to done in 20 years. But in fact, it's more than that, as you will see. DOE should move forward now to foster the creation of national teams, including public-private partnerships that will develop conceptual pilot plan studies and technology roadmaps that will lead to an engineering design of a pilot plant that will bring fusion to commercial viability. And this whole matter of public-private partnership is not something that the community is dreaming about. There are already some very good examples of that happening. It's already happening in MIT. It's happening to an extent in Princeton. It's already happened in Tri-Alpha on the West Coast. And I can give you several such examples that are already underway, but we need more of it. And the conclusion is of the report that successful operation of a pilot plant in the 2035 to 2040 timeframe requires urgent investments by DOE and private industry, both to resolve the remaining technical and scientific issues and to design, construct, and commission a power plant. The urging to the community is to finalize such a design, while it is also going to be improved in subsequent years, in the next 5 years. How challenging is this vision? Harold Grad, a very eminent plasma physicist and applied mathematician who worked at the foundational aspect of things, so he has perhaps a lot in common with people like Jim Simons and others who were grounded in mathematics and made a profound difference to the life of plasma science. Reflecting on how hard he thought fusion was, and he was not given much to exaggeration, very conservative in stating his ideas, but on this he said things that you might think is a little exaggerated. He said, a reasonable analogy for the fusion energy problem would be a mission-oriented program to land a man on the moon, which we have done that. But whereas part of the project, one must at the same time discover and exploit Newton's laws of motion, Maxwell's equations, electronics, and solid-state physics. Now that is a tall order, and fusion physicists certainly can claim to have done all of that. But it is a reflection on the magnitude of the difficulty of the problem that Harold ended elsewhere by seeing that the theory problem was extremely hard, and the experimental problem was even more so, much more so than the theorists, and the theorists had a hard enough task. So we are apparently, as theorists, have an easier time of it, and we are dealing with extremely hard problems. Why is the problem so hard? Because the plasma and nature is insidiously clever. People thought, and some of the best in the community, and you will hear some of these names as I go forward, underestimated how difficult plasmas are to control. So magnetic confinement, which is the crux of our talk today, is not the only thing that people have tried. They've also tried inertial fusion, fusion by laser light. The largest experiment of this nature is at Lawrence Livermore Laboratory, where you actually see a capsule, a spherical capsule, which is irradiated by lasers, which attempts to compress it, either directly, hence called direct drive, or through reflection on the Hall room, which is hollow space where the capsule resides, and one tries to compress this particular capsule by reflection of laser light. A beautiful image of that is really this Hall room, which I just showed you, the indirect drive object that you saw the picture of, and that's what it is in the scale of the human eye. But computer codes have tried their best to model what compression uniformly would look like. And one of the reasons why the National Ignition Facility has such a difficult time controlling nuclear reactions is because of Rayleigh-Taylor instability and its variance. And so here you see, in the context of inertial fusion, the bane of controlled thermonuclear fusion is that we have plasma instabilities. I won't have more to say about inertial fusion except to say that very talented group of people are working on exactly that in order to get another approach to fusion going. But today our focus primarily will be on magnetic confinement. When you're thinking of magnetic confinement, what you're thinking about is the first thing that you can think of, for those of you who know, remember your freshman, sophomore physics, that if you have a charged particle and if you have a straight magnetic field, that charged particle moves dominantly along the field line while it traces out helical paths. So it would seem like if you have uniform straight magnetic fields, by doing this, you have more or less guaranteed perpendicular confinement because they just wander to the extent of a Larmor radius away from the magnetic field. But the problem with this particular configuration is that it would make for a prohibitively long plasma, one that is simply impractical if you're going to compensate for the end losses in such a system, which will be enormous, not enough to overcome uh, the amount of energy that you would generate by fusion in the core of such a straight cylinder. So faced with that, people felt, well, an easy solution would be to take that straight field line and to make the cylinder into a donut. You have curved field lines then. And if you could confine particles to have helical orbits that are confined to the field line, you would be in business. Unfortunately, nature is not so obliging. It takes a little bit of work to actually show that when you actually bend a magnetic field line, even a vacuum field, you introduce what are called gradient magnetic field or curvature of drifts in the magnetic field by which the charged particles drift off the field lines that are meant to confine them. How do you then succeed? Well, from the point of view of mathematicians, a beautiful answer was given by the brilliant Noether. For those of you, I don't know how many of you are interested in the history of ideas. She was born at a time when it was not fashionable for women to be in science. For someone even as brilliant as she was, and it was through David Hilbert and Albert Einstein's intervention that she actually had a non-paying lecturer's job. Fortunately, that gave her enough of working space that she produced some of the really important mathematical discoveries in algebraic topology and other things that have outlived her. Noether's theorem, or Noether's theorem, is that for each continuous symmetry of a system, there is a corresponding conserved quantity. Well, that's very valuable insight. What that means is that if I take that torus and I build it to be symmetric in the long way around, there will be actually a conserved quantity. And what is that quantity? It is the canonical angular momentum written in terms of the charge of the particle m. V phi is the angular speed. R is the so-called major radius of this torus. And A phi is the phi component of the vector potential. The vector potential can be one through which the magnetic field can be defined, because if the field is divergence-less, which you have learned from your freshman and sophomore physics, then B can be written as the curl of a vector potential. It is that vector potential that enters. Now, if you're looking at very strong magnetic fields, and that is what we tend to do because we would like to confine the charged particles as close to the magnetic fields as we can, like beads on a wire, you would want to make the magnetic field much stronger than momentum. If you do so, then the particles will be stuck to surfaces of constant r times a phi. And this is what is shown here, a bunch of nice nested surfaces going from the axis of this torus outward, and particles will in general be tied to it by the strength of Noether's theorem. Okay? What is happening to these surfaces is that the field lines are filling them densely. So if you are on a particular point on this surface and you follow the field line, you'll go round and round and round, and it will not bite its tail on most irrational numbers or surfaces until it fills the surface completely. The only places where the field lines will bite their tails are the so-called rational surfaces, which are actually places which you need to watch out for in terms of plasma instabilities. But that's a separate topic. What you have here, therefore, is not just a toroidal field that closes on itself, but a superposition of a toroidal and a poloidal field that allows the field lines to be helical in such a way that they fill these surfaces. This then gives you what is called a twist, what is called the rotational transform, and that's a very important idea in fusion physics. The trouble with the axisymmetric configuration, though, even though it's a very elegant solution, is that it's a problematic solution in part. Nonetheless, that one we have pursued assiduously is that once you are given that symmetry, you write curl B equals mu 0 J, and you impose that you have axisymmetry and that you have nested surfaces labeled by RA phi, is that Ampere's law tells you that you must have a J phi, which means that the magnetic field lines that you're seeing here, or the particles that you see in blue that are going back and forth tied to this surface, and you can see these lines, they're helical, they're going round and round, but in order to sustain this configuration, you actually need to impose a current density. This current density is the source of major instabilities in plasmas and can cause disruptions. People have known and studied this device. It is called the tokamak. It is, in fact, the leading fusion concept at the present time. We have two major facilities, D3D in General Atomics at San Diego. The right-hand side shows illuminated plasma in D3D. And this is an STXU, which is having a new life after some setbacks, and it's well on its way to being rebuilt and should be operational in a couple of years. But operational on the way already also is ITER. There's a cartoon of ITER, and it is the first burning plasma that will actually be producing more energy, 10 times the energy than it takes to get it started. Hence, it is called Q equals 10. It has an input of 50 megawatts. It's supposed to have an output of 500 megawatts. No electric power yet, but definitely a power multiplication factor. And one would hope, and one is planning for ITER to have this target somewhere around 2035, even though the plasma itself would be operational beginning 2025. And we strongly hope and believe that ITER will be successful. Nonetheless, in order to get there, it has to deal with two major challenges. One, which worries a lot of people, is that the plasma current is a source of disruptive instabilities that can produce highly energetic runaway electrons, which can damage confinement vessel. This would make running with ITER at the enormous currents that it is operating in impractical as a regular power source. Second is that in order to achieve steady state operation, you'll have to impose strong current drive. These limitations notwithstanding, ITER is no longer just a cartoon, far from it, and you now see the ITER campus in Cadarache, and I've paid more than one visit there. I recommend to all of you to go and see what a spectacular experiment looks like, and the central building that you see here is where much of ITER is coming together. It's the largest toroidal fusion facility ever built, and it's really worth seeing, awe-inspiring for people who like fusion. Lyman Spitzer, when he inaugurated the fusion program, a very well-renowned astrophysicist, was trying to envision a fusion plasma which could operate without plasma current, operate in steady state. In that, apart from thinking of things that uh, takes significant intuitive genius to come up with. He not only fathered the fusion program in the US, he built the Princeton Plasma Physics Laboratory and also had a major role in building the Department of Astrophysical Sciences as we know it today. The first important idea that Spitzer had, who was an avid mountain climber, apparently the idea came to him on the top of a mountain, is that if you actually take a torus and you twist it into a figure eight, that means you start out with simple toroidal field, no current, okay? That's a donut toroidal magnetic field, and you twist it into a figure eight, you will automatically, for purely topological regions, generate a poloidal magnetic field. And that poloidal magnetic field combined with the toroidal magnetic field would generate a rotational transform, a twist in the magnetic field that will confine charged particles. This was truly ingenious and in many people's minds, the most beautiful topological idea for magnetic fields that the fusion community has ever thought of. And it turns out that he anticipated the Berry phase in quantum mechanics by many, many years, one of the first anticipations of the Berry phase. But moving on, the classical stellarators, be it the figure eight or whatever it was, didn't do all that well because the first time these machines were built, there was less of an appreciation on how sensitive they were to coil tolerances and so on and so forth. And people were then also trying to learn the art of controlling plasma instabilities. Together conspiring, they did not have great numbers to show for their experiments, even though the idea itself was a very powerful one. The idea underwent a further renaissance much later, thanks to the work of Alan Buser in 1983 and to Nuremberg and colleagues in Germany, is that if you look at the particle Lagrangian in a magnetic field, neglecting the electric field, and most graduate students and undergraduates in physics know about this, the first term is the non-relativistic kinetic energy term. The second term comes from the magnetic field term. We are for the time being neglecting electric field, which is negligible compared with the size of these other terms for charged particles in magnetic fields. Now, if you actually take this Lagrangian, and if you imagine you have a very strong magnetic field around which the particles are gyrating very rapidly, and if you actually average out that very, very fast gyro motion, whereby you're really describing the motion of the so-called guiding center along the magnetic field, you can describe it using this approximate Lagrangian or average Lagrangian. What Alan Buser pointed out very shrewdly was that this Lagrangian itself does not depend on the vector magnetic field B, but actually on the magnitude of B. This gave rise to the very interesting possibility that whereas the vector magnetic field could be dependent on three coordinates, if we were clever enough to write the magnetic field in a fancier coordinate system, which has come to be known as Buser coordinates, then it is possible to imagine a situation where even though the magnetic field would depend, the vector form of it would depend on all three coordinates, the magnitude of it won't. And then if there is a symmetry direction, because Noether told us that if there is a symmetry, a continuous symmetry, there will be a conserved quantity, then even in 3 dimensions, if the magnitude of B, say, is independent of phi, then you would have a 3-dimensional device which will be subject to a conservation law, and that will keep the particles in the system. Or not just axis symmetry, there was another helical symmetry that you could also have that would also give you this property. So the question that you could ask yourself is, can you actually make a non-symmetric vector magnetic field with symmetric B? We call this a hidden symmetry because it is not obvious if you write these terms in terms of the simple Cartesian or cylindrical coordinates that we all love. But if we can write these things in Buser coordinates, you'll actually see this symmetry manifest. The question then is, can I start with a vacuum field with curl B equal to 0, eliminate most of the internal current in a plasma with finite pressure? And rather amazingly, the answer turns out to be a yes. And the fact that this can be done was actually shown, albeit with helical symmetry, by the Madison experiment, the HSX experiment, so there are two forms of quasi-symmetric stellarators that we are talking about. Stellarators distinguished by lack of plasma current. One are quasi-axisymmetric stellarators, which have the property that del phi of the magnitude of B is zero. The other kind is del of a helical angle of the magnitude of B is also zero, and that's the kind that the Madison experiment is about. And here written, this made explicit, is that this is a measurement of the magnetic field in this helically deformed HSX experiment, and you see written in these helical coordinates, the magnitude of B are straight lines. So they are uniform as long as you move along the direction of helicity, which intersects the theta phi plane along a particular direction. What does optimization do? Well, surely the tokamak is a very simple case of quasi-symmetry. And in that, the particles are very well confined, as this movie will show you. In the classical stellarator, this issue wasn't dealt with as carefully as it needed to be. Particles were confined up to a point, but if they hung around long enough, they would in fact escape. The Wendelstein 7X, the pioneering German experiment that I will be showing you some results out of, actually was designed to do this, to confine many of these particles. And here you actually see the optimized W7X design, which was not exactly built to be a quasi-symmetric stellarator, but was used an idea that is close enough to it. And I won't have the time to go into variants of that. But basically the idea was something similar. Use the computer to design a magnetic bottle in which particle confinement is actually superior. They accomplished that. In fact, this is a picture of the Wendelstein 7X experiment, which is the most successful stellarator experiment. This was out of the first results that came out back in 2015. They eventually planned to produce about 30-minute plasmas. These are, in fact, the magnetic surfaces. These are the coils. I know they look crazy to you, but they have been built and engineered. And what is remarkable is that using today's technology, these coils can be built with great precision in a way that actually works as the computer predicts they should. And to demonstrate that, I want to show you some data points from stellarator fusion performance. And the cardinal quantity in these cases is really two things. One is how hot the electron and ion temperatures are. So you're looking at electrons and ion temperature curves. The density is increased by pellets, but you can actually, by suitable design, suppress the turbulence by optimizing the stellarator, and I'll show you what that looks like. They put in some power, 5 megawatts of electron cyclotron resonance heating. They realize electron densities, ion and electron temperatures of about 3.8 keV, energy confinement time, this. The record triple product for stellarators is this number. This is not only 15% higher, and this is what is shown here, than the previous stellarator record, which was held by the stellarator in Japan, the LHT device. It was achieved at temperatures 8 times higher, much closer to the fusion regime of 8 to 40 keV. There's a lot more data that I can show that, precious though the data points in W7X are few compared with what the tokamak database is, what we already have in the stellarator database is very promising for the future of stellarators. How did we achieve this? And I'm speeding up just a little bit, and this is where the optimization program that we are undertaken in the Simons Mathematical and Physical Sciences collaboration is already beginning to have an effect. It's important to recognize these parameters were achieved only because the W7X optimization was successful and turbulence was suppressed. For the achieved temperatures and densities in these discharges, earlier stellarator designs would have had much lower confinement times and triple products. In W7AS, which is a previous incarnation of W7X, it would have been at least a factor of 3 lower. And TJ2, which was built essentially without optimization, at least a factor of 40 lower. If this discharge had not visited the valley of stability for turbulence, and the value of stability of turbulence is this blue region, what came about because of optimization in the design. And this is what we are pursuing in the Simons Mathematical and Physical Sciences collaboration, that we are building the next generation stellarators with this lesson firmly in mind, that we need to minimize not only with particle confinement, but also with respect to turbulence. In the Simons project, we are actually pursuing optimization, improving the mathematical underpinnings of the subject, coming up with new techniques, and some of this I'm talking about. Some of this is already implemented in the form of codes. This is an optimization of a Simons Stellarator design effort, which uses analytic derivatives of the magnetic field to arrive at converged solutions where you get good quasi-axisymmetry in the core to a very high degree of approximation. And you get good flux surfaces, vacuum surfaces, out to ratios of nearly 2. A stands for the ratio of the major to the minor radius. Furthermore, using these techniques, we can now actually generate, and this has been done now, 240 million quasi-symmetric stellarators with very little computer time. This map was utterly impossible a few years ago. And what is really interesting, if you look at this map on the maximum axis curvature against rotational transforms, this is in the entire space of possibilities of quasi-symmetric stellarators. If you use the different colors to simply label the number of times the mod B contours rotate around the magnetic axis, you'll find that all the experiments are in this narrow sector of this vast sea. And this is what computer exploration enables you to do. This is what multiplicity of choices of the kind of device you want to build allows you to move around. And this is a 50 parameter space that you move around in, but now we know how to do it and to do it efficiently. It would not be appropriate if I finished a Simons Foundation talk. Sasha, I still have about 10 minutes.
Correct.
Thank you. I'd like to tell you a little bit of the mathematics of quasi-symmetry. One of the unique features that has been made possible by the Simons collaboration team is that realizing that the optimization of stellarators is a problem that brings in applied mathematics, theory of partial differential equations, high performance computing, plasma physics, nonlinear dynamics, that we have a multidisciplinary team which approaches these problems from different levels of rigor and practical attention to detail. And one of the things that has emerged in this collaboration over the last year or so is that we have fundamentally redefined mathematically what quasi-symmetry means. In the older classical Boozer-Nuremberg definition, quasi-symmetry was defined with not only the requirement that particles should be confined in the manner in which we have discussed, but they also built in into the discussion itself that one should satisfy the conditions of MHD equilibrium at the same time. And these were amalgamated together. What we have tried to do in the foundation collaboration successfully is to separate out the mathematics of magnetic fields and particle confinement altogether from the equilibrium problem. And this has some fundamental significance. In our definition, which are now called weak quasi-symmetry condition, quasi-symmetry is defined as one in which, if one can find a vector u such that u dot grad b equal to 0, which simply means that b is constant following the vector u, which is the direction of quasi-symmetry. B cross u is given by grad psi, where psi is the flux surface label, and del dot u is an incompressible condition. Then one can show that the field is quasi-symmetric, independent of the nature of the equilibrium. And this came out from the work of Berby, as well as the work of Rodriguez, who is a graduate student in the program. Graduate students are doing wonderful work in our collaboration, and that's the way it should be. It's a program that is built on the heroic efforts of graduate students and postdoctoral colleagues. These constraints are obtained, as I said, from fundamental considerations of Noether's theorem of the conservation of angular momentum of charged particles, but don't make any assumptions regarding the form of the equilibrium. Now, in the classical literature, we have generally thought of equilibrium in terms of the variational principle of Kruskal and Culsford. The idea is very simple. Kruskal and Culsford pointed out back in 1958 that if you take the energy of a plasma, potential energy, which is magnetic energy plus the thermal energy, where P is the thermal pressure and gamma is the specific heat, and you minimize this subject to the ideal constraints on the plasma, then you can always produce equilibria which satisfy J cross B equals grad P. This minimization process of minimizing energy actually underlies a lot of the codes, such as the one at the Courant Institute, VMEC, which was, pardon me, at Oak Ridge now, but was built at Princeton and elsewhere before it migrated to Oak Ridge. And STAB, which is a Courant code, pioneered by Garabedian, but then carried to further heights by his collaborators. One could do either Kruskal and Culsford, or one could do grad. One would have the same consequence, that one could have a variational way to approach the equilibrium problem. Quasi-symmetry, though, leads us with a very important further thing to think about, which is that it's not enough for us to just generate equilibria. We have to generate equilibria that also have the quasi-symmetry property. In this, actually, prior to the collaboration, our progress has been rather limited. What we have been able to show, we had been able to show that quasi-symmetry, there is no real rigorous proof of the statement I'm about to make, but using power series expansions and other physical arguments, it seemed like quasi-symmetry was not achievable globally, but achievable only on a particular flux surface. We asked ourselves the question whether this actually exhausts the realm of possibilities. So we posed ourselves the following problem. Imagine you have the variational principle of grad, and you want to superimpose on it the quasi-symmetric constraint. I gave you these three equations some time ago, and you can show that those equations are completely equivalent, necessary and sufficient for quasi-symmetry if this function ft vanishes. So what we did was, we did a constrained calculus of variations problem where we actually used a Lagrange multiplier, appended the constraints, and turned the crank. This was done by Rodriguez. Let me not belabor the algebra, just to let you know we did an honest day's work. What you find is something quite puzzling. You find, in fact, that turning the crank with that extra constraint, you get minus J cross P plus grad P, but something that doesn't go away. So somehow, by minimizing that variational principle of grads, this constraint screws us up. It gives us an extra force term. Well, this is oddly reminiscent to us of what happens in Lagrangian dynamics. The idea of doing constrained mechanical problems, graduate or senior mechanics, you know that you will write down the principle of least action, and then you will typically, if you do nothing, you will actually get Lagrange's equations of motion for the n degrees of freedom. These are Lagrange's equations. But now suppose if you actually impose holonomic constraints, in other words, they don't depend on time, then the principle of least action can actually produce automatically Lagrange's equations of motion, but on the right-hand side, you would get what are called generalized forces. Now think of the variational principle we just did. We imposed the quasi-symmetric constraint and got a new force. What does that mean? Well, it turns out that if you take that equation and you do some algebra, what you come to the conclusion is that that variational principle yields the equilibrium condition J cross B not simply equal to gradient of pressure, but gradient of tensor pressure, where the pressure of the magnetic field parallel to the magnetic field and the perpendicular to the magnetic field have to be different. In other words, quasi-symmetry, and this seems almost magical. You start out with Kruskal-Culsford or grad, You impose a physical constraint. That physical constraint pushes you towards anisotropic pressure equilibria. Those anisotropic pressure equilibria must now be taken into account. They augment the classes of solutions that you need to consider in order to possibly prove or investigate the question whether global solutions are possible. And it would then appear that J cross V equals grad P was too restricted a space to live in. Some people will say, okay, big deal, you go to an isotropic pressure. To me, though, that's a fundamental issue, and it's an issue of great interest to mathematicians as well. Konstantin, Drivas, and Ginsburg at Princeton have actually proved a theorem in the collaboration, which is actually consistent with that, but I won't have the time to go into. So what's the status of stellarators right now? Where are we? What sort of uh, innovations are we thinking about? People have not only built the Wendelstein, people are also thinking of building advanced stellarators. One such very promising idea is to use permanent magnets to build such a stellarator. Permanent magnets have the feature, and this comes out of a nice paper by Per Hellander, who is one of the founding PIs of the collaboration, and taken from a physical review letter that was published a couple of years ago in collaboration with PPPL colleagues. They make the point, in fact, that permanent magnets cannot create toroidal magnetic flux, but can create poloidal flux and rotational transform. So we will not need electromagnets and a very highly expensive technology. And so this is here a technology that will bend the curve. People have built on what we know about optimization theory to construct a mathematical recipe on how to arrange magnets. At the time when Per wrote the paper, Estelle was the design configuration that we're using. And originally, the design of Estelle needed 20 non-planar coils of different types. With permanent magnets, there was a significant technological simplification of only 8 identical circular coils, and this was shown to be feasible. But the project has gone a lot beyond that now. ARPA-E would actually like PPPL to pursue this program, and David Gates is a principal investigator of that. What ARPA-E wants to do is to retire the risk of building these coils, and you can see that the CAM designs of the first coils have already been developed. They have these drawer-shaped uh, magnet constructions, which seem to be quite robust in their design. They're also simpler to assembly. It's like tucking letters into a mailbox. And so this project is well underway, but the ARPA-E project will not allow us to build a whole stellarator, simply show that a coil is possible, and one is still hoping that this will someday be a stellarator. There's another really exciting idea of building stellarator with high temperature superconductors. And this was pioneered by MIT. At the central part of this, what is sitting is the so-called ARC tokamak that is presently under consideration by CFS and MIT partnership. It's radius R equals, and so this is actually one that builds on both W7X and the possible success of ARC. The parameters are given here using Repco coils going to toroidal fields of the order of 7.5 Tesla. The numbers are given here, building on the ARC collaboration. And there's a lot of thinking among people who are already thinking ahead on what sort of a stellarator would we build, reactor would we build if we took advantage of HTSC technology. So I want to come to the end of my talk. I apologize for going a few minutes over. The quest for controlled thermonuclear fusion has brought the plasma science and engineering community to the point where it is poised to finalize the design of a fusion power plant in the next 5 years. Only a design. The plan is agnostic about concept. The proposed report suggests that DOE and private industry should cooperate to produce a fusion power plant by 2035 to 40 en route to commercial viability. The power plant should have generating power of 50 megawatts electricity and total overnight construction cost of $5 to $6 billion. That is the cost constraint that this group has set for the project. The tokamak concept undoubtedly, because of its rich database, has a head start. ITER operation will provide valuable knowledge along the way to retire the risk for tokamak operation, such as disruption, one hopes not destruction, and to realize Q equals 10 burning plasmas. Stellarators have important advantages as fusion reactors. They can be steady state, no current drive, no disruption. The challenge is that we need optimization, but this can be done using sophisticated methods and powerful computers. The coils are complex, but W7X demonstrates that once these coils are built, the machine performs as projected. And last but not least, this journey has not been without its rewards. Along the way to fusion, the plasma science and engineering community has produced fundamental knowledge that has impacted applied mathematics and computational science, astrophysics and the space sciences, and low temperature plasma mediated technologies that support sustainability on Earth. I'd like to end by thanking Jim Simons. He has made the decision to step aside as the president of Simons Foundation. And I'd like to quote him in this New Yorker article, and something that Jim has done better than any philanthropist I know, which is to support fundamental science. So taste in science, he says, is very important to distinguish what's a good problem and what's a problem no one is going to care about the answer to anyway. That's taste. And I think I have good taste. And Jim rightly showed good taste in investing in Stellarator fusion and allowing us to pursue some of these exciting research directions. So thank you, Jim.